Modeling using the data from production management systems. The most widely used production management information system in practice are MRP2 and ERP. Data stored in those systems can be used to build up a detailed model of the production system with Petri Nets. In discrete manufacturing, these data are bills of material and routing, while in batch manufacturing, master formula and recipe are used to determine the production process. Work orders are used to determine which and how many of finished products have to be produced. The bill of materials, BOM, is a listing or description of the raw materials and items that make up a product, along with the required quantity of each. In batch manufacturing, other terms are used instead, i.e. formula. The BOM used in this work is defined as BOM equals R, E, Q, pre, where. R equals R1, is a root item. E equals E1, A, is a finite set of subitems. QE is the function that defines the quantities for each subitem A. Q represents an I times 1 column vector whose ith entry is QA. Pre, E times E0, 1, is a precedence constraints function. It defines the precedence constraints matrix pre, where pre-I, j equals 1 indicates that the ith item precedes the jth item. It can also be interpreted as a directed graph. R is a root item and represents the product that is composed of subitems described with AE. The number of required subitems is determined with the vector Q. When any subitem has to be produced before another, the precedence function pre is used to define it. All the subitems have to be finished before the operation for the subsequent subitems can begin. A required property of pre is that only zero values can be on its diagonal, i.e. a subitem cannot precede itself. An item is never allowed to become, indirectly, a component of itself. In other words, if the BOM structure is seen as a directed graph, this graph should be cycle-free. If any of the subitems A are composed of any other subitems, the same BOM definition is used to describe its dependencies. The items at the highest level of this structure represent a finished product, and those at the lower level represent raw materials. The items that represent raw materials do not have a BOM. Table 1 shows an example of a BOM describing the production of product I, which is composed of 3 components, i.e., 3 items of J, 1 item of K and 2 items of L. From the precedence constraint matrix, it is clear that all of the items J has to be completed before the production of item K can begin. Example of the BOM structure. The mathematical representation of the BOM of item I would be represented as. To start with building a model, let us assume that, for each item from the BOM, only one operation is needed. As stated before, each operation can be represented with one place and 2 transitions. To be able to prescribe how many of each item is required, the transition tran and the place pran are added in front, and prout and trout are added behind this operation. The weight of the arcs that connect tran with pran and prout with trout are determined by the quantity Q0 of the required items. In this way, an item I is represented with a Petri net as defined in PN structure representing one item in the BOM. As finished product is defined with a structure of BOMs, the construction of the overall Petri net is an iterative procedure that starts with the root of the BOM and continues until all the items have been considered. If the item requires any more sub-assemblies, i.e., items from a lower level, the operation, the framed area of the PN structure presented in, is substituted with lower level items. If there are more than one subitems, they are given as parallel activities. The substitution of an item with subitems is defined as follows. Remove the place PI up and its input/output arcs. Define the PN structure for subcomponents, as it is defined with a BOM. Consider the precedence constraints. Replace the removed place PI up by the subnet defined in the previous step. The input and output transitions are merged with the existing ones. The result of building the PN model of this example, Table 1, is given in, where item I is composed of 3 subitems, J, K and L. BOM structure defined by PN. For each item that can appear in production process, and does not represent a raw material, a routing is defined. It defines a job with sequence of operations, each requiring processing by a particular resource for a certain processing time, which are needed for transforming raw material into the subproduct. This information are provided by routing tables in discrete manufacturing, and by recipes in batch manufacturing industries. The table contains a header, where the item that is being composed is defined and the lines where all the required operations are described. For each operation one line is used. As an example, the routing table for item K is given as presented in Table 2. 3 operations are needed to produce this item. The first of these operations can be done on 2 different resources. Similar notation is used for other possible cases, for example an operation that needs 3 resources R1 and 2 R2, or 1 resource R1 and 3 R3 would be presented by 3 times R1, 2 times R2, R1, 3 times R3. Routing of product K. The implementation of the routing data in one item of a BOM is defined as follows. Remove the place PSOP and its input/output args. Define a PN structure for the subcomponents, as it is defined with routing data. Also precedence constraints are considered here. Place PSOP is replaced with a subnet defined in previous step, where input and output transitions are merged with the existing ones. Function that defines PN structure for every subcomponent yields the corresponding sequence of production operations from the routing table, and for each operation a timed Petri-Net is built as defined in section 3.3.1. All the placed operations are connected as prescribed by the required technological sequence, and each operation is assigned to the required places representing appropriate resources. Routing of product modeled with timed Petri-Net. The PN structure in is achieved if the sequence of operations described with a routing table, Table 2, is modeled. The resulting PN structure is inserted into the main PN model, on the place where item K, PCOP, was. The routing/recipes are submodels that are inserted, by substitution, as defined previously, into the main model defined with the BOM structure. However, some activities of any subitem may also be described with a BOM, i.e., in the case they are composed of semi-products. The construction of the overall Petri-Net model can be achieved by combining all of the intermediate steps. The work order, WO equals, determines which and how many of the finished products have to be produced. Each product, R, can be represented with a Petri-Net model, shown in, where one place is added in front and one at the end of the structure to determine the start and end of the work. As usually more products are produced at one time, one product is represented with one batch. The weight of the arc that connects T-RIN and P-RIN are used to determine the number of required batches, Q0. To be able to consider different starting times for different quantities of one product, the general structure shown in is used. Q0 determines the number of products to be finished. Orders for products which should start with the production at the same time are merged, and every group of products with the same starting time is modeled with places P1, P2, PN and with tokens located in them. The timestamps, which are assigned to these tokens, determine the starting time of every group of products. Whites Q1, Q2, Q1 determine the number of products, where Q1 plus Q2 plus ... plus Qn is equal to Q0. The token in the place pinned implies that WO is finished. Petri-Net structure of a work order.